Okay, here we go with the new unit. Um, this stuff, a lot of it is going to be a review for you guys. We're just going to talk about it a little bit more in depth than we did last year and do a little bit more in-depth calculations. But honestly, this isn't this particular section is not a huge part of the AP exam either. So we're gonna go through it fairly quickly here. And I will be honest with you. Again, this leans more to the physics side of things, which is where I'm a little bit weak. And so my explanations may not satisfy all of you. And if you want to talk more in detail about it, maybe we can talk about it. Maybe I will know the answer, maybe I won't. But we're going to go through as much of this as we can, and I'm going to try and make it as clear as I can as we go through it. Turns out, understanding the atom is it's necessary to understand waves before we can really understand the atom. And that seems a little bit weird because up until, the turn of the 19th or the 20th century, I guess, physicists and chemists would have kept those two categories separate. Atoms are made of matter, not energy, and so we don't talk about waves when we're talking about atoms. We talk about mass, we talk about volume, we talk about those sorts of things, and then with waves, like light, that sort of thing, that's when we talk about wavelength and amplitude and intensity and those sorts of things. Turns out there's a little bit more of an overlap there than scientists realized at that point, and that especially is true when we start talking about electrons. So that's really where this is kind of going. So as far as waves are concerned, when we have a wave, like a light wave, electromagnetic wave, or a sound wave, sound wave is not as good as an example because that's more of a compression wave. But any sort of sine wave here, like this, you're going to have a wavelength that is the distance from crest to crest, and then the amplitude is basically the height of the wave from the center of that wave to the top. Okay, and so those are a couple of terms that you might want to just be familiar with when they're talking about it. They're never going to ask you to calculate the amplitude. I've never seen that on an AP exam. They might ask you to calculate the wavelength in the context of frequency or something like that, but it's a good idea to know what those two terms mean. Okay. All right. So you can see the distance between corresponding points is the wavelength, and there's no really blanks to fill in on this, so I guess I can go pretty fast here. The number of waves passing a given point is frequency. And so, as you can see, the one on the top here has a higher frequency because there are more of those waves. If those waves were moving past you, you would see more of them go past in a minute than you're going to see of these going past in a minute, okay? And so, these up here, if you measure their wavelength, it's going to be shorter, okay? Lower wavelength, but they're going to have a higher frequency. I'm just going to put F. Lower wavelength, higher frequency. And then down here, they've got a longer wavelength, but there's going to be less of these passing you at any given time, so it's exactly the opposite. These have a longer wavelength, and they have a lower frequency. Okay? And that's for waves traveling at the same speed. Okay? So then when we're talking about electromagnetic radiation, these are the different types of electromagnetic radiation that we have. This chart is arranged in order of increasing wavelengths. As you go across, the waves get longer. And the longer the waves, the less damaging the radiation is, and the less energy that it has. Okay, so you look over here, gamma rays. We talked about those a couple units ago when we were talking about nuclear chemistry. Those have the shortest wavelengths, the highest frequencies, and the highest energy, and that's why they mess you up when they go through you. Okay, radio waves, over on this side of the spectrum, they have a very low frequency because they have very, very long wavelengths. In fact, these, this is in meters, and notice here, this is 10 to the third meters is what we're talking about for these kinds of waves. So they're very, very long. And then right in the middle of that, you have the visible spectrum, The visible spectrum is, visible light. And so every color light that we can see, including white, that's going to come from the visible spectrum. Now, white is going to be a combination of all of the colors hitting our eyes at once, and that's what white light is. Okay. All this electromagnetic radiation travels at the same velocity, speed of light. Okay, so a radio wave, a gamma ray, they all travel at the same speed. So the only thing that's different about them is their wavelengths, their frequency, and their energy. Okay. So let's see here. Oh, I guess I need to go back for your first sample problem. Sorry about that. So the question here is, for the two waves represented above, which one has the higher frequency? I guess we did answer that. I didn't realize we were answering that. But this one up here has the higher frequency. And it says if one wave represents visible light and the other represents infrared radiation, which is which? Okay, now we might want to come over here for a second and just look at this. If one is visible and one is infrared, the infrared is going to be the one that has the longer wavelengths, 10 to the negative 5th as opposed to 10 to the negative 7th or 10 to the negative 6th. Okay, so the infrared would have longer wavelengths and a little bit less energy. So then if we go back over here, this one down on the bottom, that's probably the infrared, and then the one up here would be the visible light. Okay, alright, moving on. So, let's see. Okay, therefore C equals lambda times nu. Okay, wavelength times frequency. So if you multiply the wavelength times the frequency, then that's going to equal the speed of light. Okay, and that's actually a very useful equation, because then if you know the wavelength, since the speed of light is constant for all of these waves, if you know the wavelength, you can calculate the frequency. Is it saying velocity? I meant to say frequency. This is wavelength, and the V here is frequency, not velocity. Okay, so if we know one, we can calculate the other, and when we're talking about electromagnetic radiation. Alright, now let's do something real quick here. I want to go over the sample problem that you have on your notes. I don't know why it didn't end up on my PowerPoint, but I'm just going to show it to you on here. So, it says the yellow light given off by a sodium vapor lamp used for public lighting has a wavelength of 589 nanometers. What is the frequency of this radiation? Okay, so we know that C equals lambda times nu. And the lambda here, that's our wavelength. And the nu is our frequency. Okay, and so we know the wavelength, and we need to find the frequency. Okay, now the thing is, the speed of light is, you got to pay attention to your units here, 3.0 times 10 to the 8th meters per second. Okay, and that's equal to, our wavelength here is 589 nanometers, but we need that to be in meters. So 589 nanometers. I don't know if you remember this conversion or not. It might be a handy one to know for this unit, because we talk about nanometers a lot. Go from nanometers to meters. In 1 meter, there is 1 times 10 to the 9th nanometers, or a billion nanometers. So we're taking 589 divided by a billion here. And that's 5.89 times 10 to the negative 7th. Okay? So 5.89 times 10 to the negative 7th meters times nu, or our frequency. That looks like a V. It's nu. It's the Greek letter nu. But you can call it V if you want. It's just easy to confuse with velocity if you call it a V. And really, the velocity that we're talking about here is the C in this one, speed of light. Okay. So then we just need to figure this out, solve for nu. And when we do that, 3 times 10 to the 8th divided by 5.89 to the -7th. This is 5. These are 3 sig figs. 5.09 times 10 to the 14th. And then we need to talk about units for our frequency. I don't remember if we talked, I think we talked about this last year. So the units here are, you can say them one of two ways. Seconds to the -1 is one possible unit there. The other way to say that is hertz, Hz, equals 5.09 times 10 to the positive 14th hertz. And a hertz is the same thing as the second to the -1. So either way you want to write that is fine. But that's the frequency at that particular wavelength. Okay? Alright, back to the PowerPoint. So now we come to the part where I'm not exactly completely able to explain how this all worked. What I do know is, just historically, when physicists were trying to do calculations using the physics of the day, that assumed that everything was continuous, their numbers weren't working out correctly when they were trying to figure out, okay, if we put this much energy in, this is how the object should glow. This is the color it should glow with, you know, and how that corresponds to the temperature. They didn't have a good formula that really explained that. It wasn't working out correctly with the physics of the day. So a guy named Planck came along, and he actually was able to explain this if you made the assumption that energy is not continuous. In other words, that it comes in these packets called quanta. That's what he called them, and that's just like a specific amount of energy. And so there can be no energy in between those specific amounts. And this is what he assumed. And it was a weird assumption. You know, everyone had always assumed, well, you know, you can have any energy. Energy is a continuum. It's, I don't know, it's a ramp, not a staircase. So in a ramp, you know, you're climbing up, and your distance increases, or the distance of that ramp increases continuously, right? But what Planck said is it's more like walking up a set of stairs with energy. You can be on one step or you can be on the next step, but you can't be in between the steps, okay? And so a lot of people were like, well, that's just very strange, but he was able to show that it actually worked. And so, you know, he was able to develop a lot of equations, and those equations, when tested against reality, predicted reality a lot better than the physics of the day. So that's why Planck's ideas were accepted. Now Einstein took this, and he said, okay, now I can explain something that we've been wondering about with shooting light at pieces of metal, and it bounces electrons off. And so what he basically said was, well, here was the problem, okay? Now as they were, and again, I think I sort of explained this last year, but not very well, because this is just not my area of expertise. But the idea here was they were shooting light at this metal. And let's say that they were shooting, I don't know, low energy light. So we're talking like red light. They're shooting red light at a piece of metal, okay? And it didn't matter how bright the red light was, how intense the red light was. They made it brighter, they made it dimmer, whatever. It wouldn't bounce the electrons off of the metal. But then they used, you know, blue light, and it also didn't matter how dim or how bright it was. If it was blue light, it would always bounce the electrons off the metal. Okay, and so they could actually see, they could measure the voltage here, because if the electrons get knocked off the surface of the metal, now you have this higher flow of electrons here, and it can sort of show, okay, there is actually some additional current being provided here because this light is hitting this thing. And so what they realized was it's kind of the color of light, not the intensity of the light, that actually matters. And that was very strange. Einstein said, well, okay, so each color of light must correspond to a certain amount of energy. Okay, and it must take a certain amount of energy in order to knock these electrons off. And so he said you've got to think of this energy sort of as, he called them photons. Okay, it's these little packets of light energy, and these little packets of light energy are coming in, and they're hitting the electrons. And if they have, they're sort of being absorbed into the electron. Now, if they have enough energy, they knock the electron off. Well, none of the red light packets or photons have enough energy, so they can't knock the electrons off. No matter how many of those photons or little packets of light are hitting the metal, none of them have enough energy to cause the electrons to be emitted off of the metal. But you get some green photons or some blue photons that have a little bit higher energy, and those hit the electrons. As soon as they hit an electron, they give the electron enough energy to escape from the metal, and it bounces off. Okay, and so that was his idea. Hopefully that kind of makes sense. The main thing that you need to know here is that he decided energy is proportional to frequency. Okay, so he said the energy of this light is closely related to the frequency of the light, and he actually used Planck's constant here, which this is on your equation sheet, by the way. You might take a look at this at some point while we're going through these notes, just because this has a few of the equations on it that we're talking about today. And if the equations are on the equation sheet, then it's fair game for them to ask a question about this on the test, on the AP test. So Planck's constant is 6.63 times 10 to the negative 34th joules times seconds, according to your equation sheet. And if you remember, frequency is seconds to the negative 1, so joules times seconds to the negative 1. Well, this just cancels and we're left with joules, and that gives us our energy. Okay, so Einstein basically said we can calculate the energy of a photon of light based on its frequency. Okay, he said those two things are related. So red light is always going to have less energy. A photon of red light is always going to have less energy than a photon of blue light. That sort of thing. Okay. Oh, I wrote Planck's constant. I didn't realize it's right here. So there you go. And this is supposed to be a time sign. Joules times seconds. I guess I was too lazy to put that in. Okay. So, have we gotten to another example yet? Yes. Calculate the energy of one photon of yellow light whose wavelength... Well, okay. Actually, I gotta talk about these first. So if we know E equals h times nu, that's frequency, the energy equals Planck's constant times the frequency, and if we know that the speed of light is equal to the wavelength times the frequency, well, the thing that's in common in both of those is the frequency. So you can actually rearrange these equations if you need to, substitute some stuff in for the nu, and then you can relate wavelength to energy as well, if you ever need to do that. Okay, and actually, turns out you need that for this this sample problem here. Okay, so let's think about this for a second. If we solve the top equation for frequency, we end up with nu equals speed of light divided by lambda. Okay, and so we can actually plug this in for nu in this bottom equation, and we end up with E equals hc over wavelength. Okay, and so that's an equation that will help us to calculate the energy when we know the wavelength. All right, so let's go back here. Okay, so we've got a wavelength of 589 nanometers, which actually is the one that we had from before. Now, the nice thing about this is we already did this conversion, 5.89 times 10 to the negative 7th meters. Okay, so remember, we just figured this out. E equals hc over lambda. Now, actually, let me look at your equation sheet. That might be on there. It is not. Okay, so the two equations that are on there are the ones that were on the PowerPoint. Okay, these two right here. Those are the ones that are actually on your equation sheet, and so you do need to know how to rearrange those to get this equation. or you might, if they ask you this sort of question, okay? So, if we know the wavelength is 589 nanometers, we want to calculate the energy there. Energy equals Planck's constant, which is 6.63 times 10 to the negative 34th, I believe. I don't have that number in my head. Times the speed of light, which is 3.00 times 10 to the 8th meters per second. And we divide that by the wavelength that we know, which is 5.89 times 10 to the negative 7th meters. Then that should give us the energy. So once we calculate all that, should get an energy of about 3.38 times 10 to the negative 19th, and that's joules. And that is a very small number, but we're talking about 1 photon of light, so it makes sense that it's small. Okay. All right. Moving on here. Another mystery. And this one, I think I understand a little bit better than some of the other stuff we've been talking about here. The atomic emission spectra. And we did this last year. We're going to do a lab on this again this year, but just because it's fun. And it's fun to burn things and see what color they change. So the thing that scientists were realizing as they burned these elements, they passed electricity through them, and they each had their own characteristic color. They realized that if they passed the light that was coming from one of these elements through a prism, it wasn't giving a continuous spectrum. There were holes in the spectrum, okay? And so when you pass white light through a prism, you get something that looks like this. You get a rainbow, okay? Continuous spectrum from red to blue, all the way across. There's this. I don't know why that's there, sorry. Okay, but when we have light from hydrogen or sodium, oh, that's why the circle's it, that's funny. So hydrogen or sodium, notice sodium, you can really only see one line, and it's right at, or right around 600 nanometers, it's a yellow line. For hydrogen, and we're actually going to do hydrogen, you get a couple of purples, a blue, and a red, so you can see about 4 different colors. And the rest of it is just dark, okay? And so that was weird, okay? It meant that somehow when these things are burning, they're not giving off all the different energies that white light normally does, and scientists couldn't figure out why that was happening. So Bohr came along, and Bohr said, well, I'm just going to accept Planck's assumption. I'm going to accept that energy comes in these packets, okay? And he said, basically, I'm going to say if this works the same way in in atoms, that these electrons can only be in certain places. They can only have certain energies, because Planck said that, only certain energies are possible. So Bohr said, all right, so the electrons can only have certain energies, and those are just the possible energies that Planck said that things could have. And that sort of explains some things pretty well. It did for hydrogen, at least. So he did a really good job of explaining the visible light colors that you see in hydrogen, and even some of the not as visible light, like the infrared and the ultraviolet and that sort of thing. So he said electrons in these permitted orbits have specified allowed energies, okay? And those are the only energies that those particular electrons can have, okay? And then he said when an electron absorbs energy, it might move from the second energy level up to the third, okay? It's not going to be anywhere in between here, okay? It has to go from the second up to the third. So it has to absorb a certain amount of energy in order to make that jump. If it doesn't absorb that much energy, it won't jump. It'll just stay where it is, okay? or it might jump from the second to the fourth or something like that. Now, when an electron falls from a higher energy level down to a lower one, and you should remember this from last year, hopefully, that is when a certain characteristic color of light or frequency of light is given off, okay? And it might be in the visible light spectrum, it might not be. You might give off, the atom might give off infrared or ultraviolet, or, if it's X-ray or gamma ray, if it's a, I don't know that any of the electron jumps can give you that kind of energy. I think you get that kind of energy from a decaying nucleus. But hopefully you get the idea. When an electron jumps from a higher energy level down to a lower one, that's when it gives off a certain frequency of light. It gives off a photon of light, okay? And so you've got this equation here. Now this equation is not on your equation sheet, so I don't think that you would probably need to know this one. I don't think. Let me look and make sure it's not hiding somewhere else. I don't know where else it would be if it's not in the... By the way, the atomic structure is the section where you would be looking for these. It's at the top of page... It's labeled page 4 on the ones that I gave you. So, yeah, it doesn't look like it's there, okay? But, interesting equation, and we worked with it last year when we did a lab, and we're going to probably work with it on the lab that we do this year as well. So we've got this RH, this is just a constant number, okay? And the Ni and the Nf, those are the initial and final energy levels, okay? And so the change in energy here would just be, you could calculate it using this formula, and that would tell you how much of an energy change you get when the electron falls from one energy level to the next, or if it's absorbing energy, when it's going from one energy level up to a higher one. Okay, do I have a practice problem on that? Yep. Using the above diagram, predict which of the following electronic transitions produces the longest wavelength spectral line. N equals 2 to N equals 1. N equals 3 to N equals 2. Or N equals 4 to N equals 3. Okay? So notice, there's a big difference in the energy of the first energy level versus the second. Okay? So you have an electron falling from 2 to 1. Okay? It seems like a lot of energy is going to get released there. Okay? If you have something falling from 3 to 2, not as much, but still more than 4 to 3. Okay? So you can kind of tell which one's going to release the longest... Okay, it's asking for the longest wavelength. That's kind of tricky. So the highest amount of energy will be 2 to 1. Okay? But if it's got the highest energy, that's going to be the shortest wavelength. So the longest wavelength would actually be this transition right here from 4 to 3. Okay? It's going to produce the longest wavelength spectral line. Okay. So we talked about the Rydberg constant. Let's talk just a little bit real quick about the wave nature of electrons here. So Einstein had basically said, and we didn't talk about this, but this is essentially what he was saying with light. He said that light can act like a particle sometimes. So these waves have particle-like properties. Okay. So de Broglie came along and he said, "Okay, Einstein, if that wasn't an insult back then, by the way, he was just saying his name. But he said, okay, Einstein, if waves can have particle properties, then I think particles can have wave properties." So he was just kind of copying. But anyway, that's what he said, and he was right. And so he didn't just say that; he was actually able to back it up with some mathematics. And so he showed that there actually all matter does have these wave-like properties. Now, again, this is in a realm where I'm not doing a very good job of understanding, but everything exhibits some wave-like properties. The thing is, most things are too big to really notice it. But when you get down to the size of something like an electron, it actually does make a difference. Okay? So he came up with this formula here. The wavelength is equal to the to Planck's constant divided by the mass times the velocity. Okay, that actually is a v. That's a velocity, not frequency. Okay, just so you know that. Okay, now again, this is Planck's constant. This is 6.63 times 10 to the negative 34th. This is going to be an incredibly small wavelength most of the time. So small that we wouldn't even be able to detect the wave-like properties of most things that have a normal size mass. But an electron does not have a normal size mass. It has a very, very small mass. So if we want to know the wavelength of an electron, it's going to be 6.63 times 10 to the negative 34th divided by the mass of the electron, which is 9.11 times 10 to the negative 28th, times the velocity, which is 5.97 times 10 to the 6th. Okay? And we would want to make sure that all of these match up. I think the mass is supposed to be in grams here. Let's see. I'm going to have to look that one up to make sure. Hang on, I don't want to get the units wrong on you guys. It might be in kilograms. Let me pause it for just a second and look that up. Okay, sorry about that. It actually is in kilograms, and the reason for that is because the Planck's constant is joules times seconds. And if you remember, a joule has the unit kilogram in it. Okay, and so when we do the mass, we've got to use kilograms. So this is 6.63. I apologize, you guys are erasing on your papers now. Times 10 to the negative 34th divided by, let's see if I can do this in my head. 9.11 times 10 to the negative 31st kilograms. And then that's going to be times the velocity, 5.97 times 10 to the 6th. Okay, and then all the units should work out. When we figure out this number, it should be 1.22 times 10 to the negative 10th. And that's meters, okay? And as you can see, that's actually, that's a wavelength that kind of matters, okay? Because that's pretty close to a nanometer. So, so actually that wavelength is significant, whereas if we had a normal mass here, you know, like 2 grams or something like that, you know, it wouldn't be significant at all. The wavelength would be so small that it's not even close to being noticeable. Okay. So that's why an electron is kind of weird. Whoops. Okay, he demonstrated the relationship was this. You got that on your paper, so I don't need to erase that. And then that led to the uncertainty principle. Okay. And what Heisenberg basically said here, he did some complicated mathematics to show that with something like the electron, it's very, very important. The size of it is very, very important. It actually means that we can't know exactly where it is at any given time. Because for a normal size object, with his equation here, the delta x is the change in position. And the delta mv is, if you're in physics, that's the change in momentum. Okay, so this is position, and this is momentum. And that's related to Planck's constant over 4 pi. So what he realized was, if we're talking about something that, you know, is the size of an electron, it actually does make a difference. It makes it much less certain. Okay, and then the example here that they give in the book, which if you do ever look at the book anymore, when you calculate this for the electron, then you actually end up with a, and you know that the speed of the atom, which we found from the last example, was about 5 times 10 to the 6th or so, okay? um, then what you can find there is that the delta x, when you plug in the electron's mass and the electron's velocity here, then we know the delta x ends up being greater than or equal to, what's the number they have here? 1 times 10 to the negative 9th meters. Okay, so if we know its momentum pretty exactly, which is this part right here, we are sure about the position to about 1 times 10 to the negative 9th meters. In other words, that's the range of possibilities, is about 1 times 10 to the negative 9th meters across. The electron is somewhere in there. Well, the problem is most atoms are actually smaller than that. So we are less sure about the position of the electron at that point than we are about the size of the atom. And we can pinpoint where the atom is. We just, based on this equation, it's basically showing us, because of the size of the electron here, it's just so small that you just can't know its position and its momentum at the same time. Now, another way that I explained this last year with a little bit less math, and again, I'm butchering Heisenberg right now, but it sort of helps it make sense in my mind. Because the electron is so small, there actually is something to the idea that just by observing where the electron is, we move it, okay? And so the idea here is, if I shine light on something, and hopefully you'll remember this from last year, if I shine light on something, that's how I see it, right? If I don't shine light on it, if I don't shine some sort of electromagnetic radiation or something that can bounce back to me so that I can sense it, how do I know that it's there? Okay, that's the idea. But the problem with electrons is they're so small that when we start shining light at it, and especially the types of light that would actually, have small enough wavelengths that we could see the electron with it, or that we could sense that the electron is there, it moves the electron, okay? Because, if you have a really big wavelength of light that you're shooting an electron, well, that's okay, but it's a big wavelength, so we still have no idea where the electron is, right? So we've got this, big wavelength light that we're shooting at the electron, and if the wavelength here is, 1 times 10 to the negative 9th, then again, that doesn't tell us anything about where the electron is in the atom. But if we shoot, higher energy waves at it like this, with a wavelength that's small enough that we could actually pinpoint, okay, here's the actual location of the electron, then we're going to move the electron just by doing that, because we're hitting it with so much energy. When the electron is small enough, it's actually affected by those photons, those higher energy photons, and it moves. So as soon as we know where it was, we don't know where it is anymore. Okay, and again, I do a horrible job of explaining that because it's not completely clear in my head. The main thing you need to know is we really don't know exactly where the electrons are. Okay, and if you know that, then you should be good. So that's it for that. I probably talked about that more than we needed to. As long as you know how to do the basic calculations here, especially the ones that involve formulas that are on your equation sheet, then you should be good to go for these sections. And this is basically just setting us up for starting to talk about electron configurations, which we're going to do tomorrow. Okay? All right, that's it for today, or this weekend. Have a good rest of the weekend. I hope the test went well for you guys. I'm upset that I wasn't here, but I guess we'll talk about it on Monday. All right, see you then.